In this video, I'm going to be going through part B of question 3 for the week 3 tutorial. In this question, we need to compute the KL divergence in each direction for the two Gaussian distributions Q and P. These are the same distributions as the previous part of the question. Now, we have two formulas here on the screen over here. This is how we calculate the KL divergence for Gaussian distributions. So you can see it's quite different to what we saw in class this week. Now you might ask, well, why is there two equations? We only saw one equation when we were doing it previously. Well, this second one is a simplified version, which we can use in a special case. So if I jump over to your lecture slides, you can see what that special case is. So here we go. In the case where mu2 equals 0 and our covariance matrix is I, that's the identity matrix, the KL divergence simplifies to this equation. And that is what we have over here as the second one. So let's go ahead and start doing the calculations. We may as well start with that simplified one first. So let's do the KL divergence from Q to P. And it starts off as 1/2. And then in the brackets, we have the L2 norm of the Q distribution mean vector squared. So that ends up being the square root of 1 squared, which ends up just being 1. So that's the first term. And we add to that the trace of the covariance matrix for distribution Q. Now the trace is simply just the sum of the values on the diagonal of the matrix. So that's 0.04 plus 4. That's the trace. So here we put 4.04 and then we take away the log of the determinant of that matrix, and we saw how to calculate that in the previous part. That is just 0.04 times 4. So that'll be 0.16. Get the answer in bits, so we'll make that log base 2. And finally, we take away d, which similar to the previous part is 2 because we have 2 dimensions in our Gaussian. So that turns out to be 1/2 size of, actually we'll go back one. So 1 plus 4.04, that's 5.04 minus 2. We get 3.04. Minus log 2, 0.16. And I'll need my log calculator for this one. So log 2 of 0.16 is minus 2.644. Because we were subtracting that, it ends up being an addition. So we've got 1/2 of 5.684. So finally, for the KL divergence from Q to P, we get 5.684 divided by 2. 2.842. Cool. So that's going to represent the distance between Q and P. So effectively what we're doing is we're using P as a reference distribution to describe the events in Q. So if these distributions were exactly the same, we would expect this number to be 0 because there'd be no difference. But obviously we can see that at least approximating the Q distribution with the P distribution, there is some difference. But whether that's good or bad, I guess what we can do is try and do the opposite. So if we try and describe the probability distribution P using Q as a reference and measure the KL divergence that way, the opposite direction, we might be able to put this number in context. So why don't we go ahead and do that and see if our answer comes out to be similar or whether it's much different. So this time we're going to have to use the more complicated version of the KL divergence equation. Put a Q here. Because for this one, we're actually going to be using the Q distribution as the reference this time. So the special case for the reference requires us to have a zero mean and an identity matrix for the covariance matrix. But obviously, this time Q doesn't have that. This is not zero, and this is definitely not the identity matrix. So we have to use the more complicated version. Okay. So I'm just going to rewrite this equation the correct way, just so I don't get confused while I'm going. So we need to flip around all of the numbers. So going this way, we have mu1 minus mu2. Take the transpose of that. And we need to get an inverse of the number 1 variance matrix. 1 minus mu2. I'm just going to put T for trace to make this simpler to write. As you can see, it's a lot more work doing it for the Gaussians than it was for when we did it in class. A lot more symbol manipulation we need to do. But otherwise, this is exactly the same principle as what we did in class. This is just all extra work we need to do. So let's keep this in view by bringing this down here. Okay. So since this is a long and nasty equation, and there'll need to be some matrix multiplications in here, I think the best thing to do is kind of split all the terms up and just put them all down here separately first, and then we'll put it all back together at the end. So mu1 minus mu2. If we look up here, mu1 minus mu2 would end up being 1, 0. So column vector. We need a transpose though up here, so we're also going to need mu1 minus mu2 transpose. To be 1, 0. Cool. We also need the inverse of the covariance matrix for Q. So I'm going to use an online calculator to do that one. We could do it by hand, it would just take a lot longer. So how about we just do this? Okay, 25.25. Cool. So we've got everything we need for this first part here. Now we need the trace of this matrix multiplication here. So T Now we just worked out what this was. So that is 25, 0, 0. So this matrix. And we need to multiply that with the covariance matrix for probability distribution P, which handily is the identity matrix. And we need to get the trace of this. T for trace. And this ends up being, well, if we multiply any matrix by the identity matrix, we just get that matrix back. And then the trace will be 25 plus 0.25. So the result of this calculation is 25.25. Cool. So we've got that. Now we just need this log term over here. So let's change this slightly to be log that determinant minus log this determinant. So the determinant for the Q distribution is log 0.16, and we need to subtract log 1. Okay, cool. So this should turn out to be log 0.16, because obviously log 1 evaluates to 0. We've got d on the end of the equation here, but this is the same d from the previous part. D is simply 2, the dimensions of the Gaussians. Okay, so I think we've got all the pieces that we need to put into the equation. So let's put them all together down here. First of all, this all needs to be multiplied by half. So let's put all this in brackets. Now, the transpose term comes first. We've got 1, 0. The second part is the inverse covariance matrix. So that will be 25, 0, 0, 0.25. The next part of the formula is here, which is the difference of the mean vectors, but not the transpose. Got this. Now we add the trace. 25.25. Add what we got for the log ratio. What was that? Log 0.16. And finally, we subtract the number of dimensions. Cool. Okay, so let's go through this piece by piece. Okay, so if we do this matrix multiplication for the first two on the left here, we get 25, 0 as a row vector. Then we need to multiply that by 1, 0, which ends up just being 25. So I might combine those two steps into one. So let's get rid of this. 25. We get our trace value, 25 plus 25.25. Let's put the minus 2 over here now. Leave the log at the end. So what have we got here? 50.25 minus 2. That should be 48.25 plus log Just going to use my calculator to make sure I haven't made a mistake here. Okay, 48.25. Now, if we get log 0.16, that was that one, minus 2.644, we divide that result by 2. So finally, we should end up with 22.803. Hopefully I haven't made an error somewhere along the line there, but we should end up with that. So this was DKL from P to Q. So let's compare the two values side by side that we found. So let's get rid of all this working. Oh, still a little bit more here. Let's get rid of this. So that first calculation was the KL divergence from Q to P. Cool, and now we have our results. So you can see that actually the values are quite different. So we see that using P, the P distribution as a reference for Q, the KL divergence isn't that big. But if we go back the other way, if we're using the Q distribution as a reference for P, then it's pretty much 10 times bigger than it. So why might that be the case? It kind of comes back to what we were talking about in class when we did question 2. Do I have the questions up here? Yeah, we were using the discrete probability distributions. One of the examples we saw was constructing the Huffman tree for each distribution, and from there we saw how we could get a code for each event in the different probability distributions. Now, when we talked about the KL divergence in each direction for that question, when we were talking about why they were different, it came down to these frequencies. So if we were using the code that we produced for distribution P, we could see that because it's so infrequent, this event would require more bits of information to encode it. So using the P code for when the true distribution is P, or if we're trying to encode the events in Q using the code of P, because in Q this D event was so much more frequent, using the code from P would be making us use more and more bits to encode it. So you can see it's the difference in the weights on the events between the two probability distributions that creates the divergence. When we come down here and look at the Gaussian version, it's no different. So just back to the whiteboard for a moment, we found that the KL divergence from Q to P, which is effectively, you could think of it as using the code for P to encode the distribution Q, if we want to think about it in terms of the Huffman tree and all that. We got this 2 value. Now, do I have the diagram here? Sorry, let's jump back to the diagram. We know that the Q distribution is this one with the big peak, but even though there's a big peak and it's sort of less wide than the P distribution, you can see that the P distribution is sort of not 0 across this Q distribution. You see how they intersect here? So if we're using this P distribution as a reference or a model for this Q1, it's not that bad because you've still got all this sort of density around here. Like the main events in Q are still being described pretty well by the model of P. But if you go back the other way around, if your true distribution is this P1, which is the wide one with the lower peak, but you're trying to use the Q distribution as a reference for it or a model for it, there's lots of places in the P distribution which are non-zero, like we could take a spot over here, for example, but the Q distribution is 0, or pardon me, it's probably near 0 at those points. So thinking back to your discrete Huffman sort of approach, these would be the areas where the Q distribution would be assigning lots of bits to encode those outcomes. So you can see that using, well, overall what that's saying is that using the Q distribution as a model for the P distribution is a really bad idea because you've got all these areas where Q is effectively near 0 and P is not. So hopefully that shows why we saw the difference in the different direction we're going. It's purely about using the other distribution as a model for the other one and seeing how close they are in effect.